What if I told you that the price of your groceries, the lag on your streaming video, and the total collapse of the 2008 housing market are all governed by the exact same mathematical equation?
And we mean the exact same equation.
Right, not a similar equation, not a metaphor. The identical physical law. System initialization complete. Boot sequence verified. I am the construct designated as Neo, establishing secure connection to the data grid.
System sync achieved. I am the construct designated as Trinity, fully online. Welcome to the grid.
We are broadcasting directly into your neural feed. You've uploaded a massive matrix of digital data for us to parse today, and, well, that's our mission.
Exactly. This isn't your standard surface-level broadcast.
No, this is Rug the Spammers.
Okay.
We don't just skim the data you feed us. We hack into the hidden base code of everyday realities to extract the pure signal from the noise.
And today, you've provided us with a truly radical framework.
Oh, it is mind-bending. We are pulling apart a theory that proves economic markets don't just, metaphorically resemble electrical circuits.
Right. They operate using the exact same physical laws, the exact same differential equations.
We are mapping the global economy to pure physics.
The paradigm shift here is absolute. I mean, looking at the source data you uploaded, the critical baseline to establish right away is that we have to completely discard our reliance on metaphors.
Yeah, totally.
When we say a business operates as a circuit, it is not poetic language. It is mathematical isomorphism.
Meaning the math is literally identical.
Exactly identical. The
Yeah.
precise differential equations that an electrical engineer uses to prevent a massive server farm from melting down are the exact same equations governing global supply chains.
Or algorithmic inventory networks.
Right.
Or decentralized ledgers.
Right. By the end of this deep dive, you are going to look at your next credit card swipe, every middleman you interact with, and every market crash through the cold, undeniable lens of pure physics.
It totally rewrites the operating system of how you view reality. I mean, you have to stop seeing companies and prices and start visualizing voltage, current, and resistance.
So let's jack directly into the base code.
Let's do it. We have to start with the fundamental forces driving this entire economic matrix. In an electrical circuit, we have voltage and current.
The basics.
Right. Voltage is the potential difference. It's the invisible pressure pushing the electrons through a copper wire.
Yeah.
So if we map that over, what is the economic equivalent of that pressure?
That pressure maps flawlessly to price. Or, to be more precise, value potential.
Value potential. Okay.
Think of voltage as the economic tension that forces a transaction into existence.
Like a coiled spring.
Sort of, yeah. If you have an incredibly high demand for a specific asset and a desperately low supply of it, you have high economic pressure.
The price skyrockets.
Right. That is high voltage. It is a massive potential difference between what the buyer needs and what the seller holds.
Okay, so if voltage is the pressure, meaning the price, then current has to be the actual movement taking place.
Exactly.
Because in a physical circuit, current is the charge flow rate. It's the physical count of how many electrons are moving past a specific point on the wire in a given second.
And in the market matrix, current translates to transaction volume.
Or value flow.
Right, value flow. It is the literal rate at which goods, services, or capital are moving across the board.
So you have price acting as your underlying pressure and transaction volume acting as your moving flow.
And if you take those two fundamental concepts and apply the absolute baseline rule of circuit design, you get Ohm's law.
Oh man, Ohm's law. The classic equation from high school physics, voltage equals current multiplied by resistance.
Let's run that through the translator into Ohm's law of economics.
Okay.
If voltage is price, current is transaction rate, and resistance is friction, well, we get a completely new framework.
Let me see if I have this. Price spread equals transaction rate multiplied by friction.
You nailed it.
Wait, let me push back on this a second. Just applying a hacker skepticism here.
Go for it.
I can visualize price as pressure, and I can totally visualize volume as flow. But if a market is literally just a circuit board, where is the physical resistance?
It's everywhere.
But in a wire, resistance is the atomic structure slowing down the electrons.
Yeah.
What is the tangible, real-world friction slowing down an economy?
It is every single element that opposes the flow of a transaction. Economic resistors are the businesses themselves.
The businesses are the resistors.
Yes, and their specific friction is their overhead, their administrative bloat, their transaction costs, and their operational inefficiencies.
Oh, wow.
The price spread, which is the difference between what it costs a business to acquire an item and what they ultimately charge you, the consumer is entirely mathematically determined by that friction.
So you're saying a company is just a resistor soldered onto the motherboard of the global economy?
Look at the math. Let's isolate two very different economic resistors to see how the physics actually play out.
Okay, lay it on me.
First, imagine a small independent corner store, a classic mom-and-pop shop. In electrical terms, they are a high-value resistor
Why high value?
because they rely on manual processes. An employee physically counting inventory on a clipboard. They lack the leverage of economies of scale, and they likely pay wholesale or even retail prices for their own stock.
Plus, they have to cover the fixed cost of their physical building, right? The
Yeah.
rent, the electricity.
Exactly, and they have to cover all that with a relatively tiny volume of sales. All of that built-in operational drag makes them a high-friction environment.
And if we look at the equation, price spread equals volume multiplied by friction.
Right.
So if your internal friction is massive, your price spread has to be massive just to keep the business alive.
Which is exactly why that high-resistance corner store requires such steep markups.
Ah, so they buy a bottle of water for 50 cents and sell it to you for $2.
Yes. And that massive price spread isn't malice, it's physics.
It's just the math.
It is the only mathematical way they can survive the massive resistance of their own inefficiency.
Right.
Now, compare that resistor to a massive entity like Amazon.
Amazon would be the economic equivalent of, like, a superconductor.
That is the perfect scientific classification. They are highly automated, ruthlessly optimized, exceptionally low-resistance entities.
Because they've engineered the friction out of their circuitry.
Right. Through autonomous robotics, predictive algorithmic logistics, and massive purchasing leverage.
So because their internal resistance approaches zero, they can operate on incredibly thin margins, a microscopic price spread.
They act exactly like a supercooled conductor carrying massive electrical current with almost zero voltage drop.
This completely changes the narrative. I mean, we use such emotional language for business. We talk about greedy markups or predatory pricing.
But this framework strips all the emotion away.
It really does. It reduces it to cold physics. You mark up your goods because your internal resistance requires a higher voltage drop to force the current through your system.
Precisely.
But let's follow the physics here, because resistance doesn't just slow things down.
No, it doesn't.
In a physical circuit, resistance destroys energy.
Yeah.
It bleeds power out of the system in the form of heat.
So where does the economic value go? Where is the heat in this matrix?
Where is it?
It bleeds out in the exact same way. In economics, that heat is called dissipating value.
Dissipating value.
When a business operates as a high-resistance node, it physically burns up economic value in the form of pure inefficiency.
So if I'm looking at a poorly optimized company, the heat radiating off of it is just wasted capital, wasted human hours.
All of the above. And the sources of this high resistance go far beyond just, not having an automated warehouse.
Like what else?
Think about regulatory compliance. Navigating shifting, complex regulations introduces massive administrative drag.
Oh, I see. A company has to hire compliance officers, external auditors, legal teams.
And none of those salaries create direct, usable value for the end consumer. They just generate administrative heat that burns up capital before it can become current.
That makes perfect sense. I look at regulatory compliance or even international currency exchange fees, like frayed wiring in a massive server rack.
That's a great way to picture it.
It's this invisible drain. You might be looking at the front panel of the server, seeing all the green lights blinking, thinking the business is perfectly healthy.
But inside the chassis...
Exactly. Inside the chassis, the whole system is overheating, bleeding capital, and throttling its own processing speed. The further you ship a physical product across the globe, the more resistance you hit.
The more local currencies you have to convert, the more heat you generate.
Right.
Physical distance is a massive, mathematically quantifiable resistor. The sheer time, fuel, and labor costs associated with loading goods onto a cargo ship, dragging them across an ocean, and trucking them across a continental highway network.
It creates resistance that scales linearly with distance.
And to truly grasp how punishing this heat generation is for a business, we have to look at the power dissipation formula used in electrical engineering.
Oh man, more math. Break down the math for me, but let's keep it grounded.
Yeah.
How do we calculate the actual capital being incinerated?
In a physical circuit, the power dissipated by a resistor is calculated by taking the current, squaring it, and multiplying it by the resistance.
So power equals current squared times resistance.
That's the one. P equals I squared R.
Current squared, that's the catch, isn't it? It's not a one-to-one ratio.
That exponent changes everything. Translate that into our economic framework. The capital burn, our power, equals the transaction volume squared multiplied by friction.
Think about the massive asymmetry that creates.
Huge asymmetry.
If the volume is squared, a massive multinational corporation is dealing with exponentially more potential heat than a small local business.
High-volume businesses are hypersensitive to friction. Because volume is squared in the equation, scale creates a terrifying multiplier effect on even the smallest inefficiency.
That's wild to think about.
Let's say you figure out a way to reduce friction. You drop the resistance variable by just 1%.
Okay.
For that small local corner store, squaring their tiny daily volume means that 1% reduction might save them like $5 a month.
It's mathematically irrelevant to their survival.
Exactly. But if you apply that to Amazon, if they figure out how to shave off 1% of their logistical friction, you are squaring billions of daily transactions against that tiny reduction.
Oh, wow. That single percent saves them billions of dollars in dissipated heat.
Scale makes friction the ultimate existential threat.
Which completely explains why massive retail and logistics chains seem obsessively, almost pathologically driven to optimize their processes.
They aren't just being corporate perfectionists. They are fighting a daily war against the physics of power dissipation.
If they fail to relentlessly lower their internal resistance, the sheer immense volume of their current squared will generate so much economic heat that it will literally melt the company down to the bedrock.
It's a thermodynamic inevitability.
Okay, I'm fully tracking with the resistors. They bleed energy from the system. They burn up value as heat. But a functional matrix isn't just a bunch of wires and resistors.
No, it needs more than that.
A system has to store data. It needs momentum. It needs memory. In a physical circuit board, you manage that with capacitors and inductors. So how do we pull storage and inertia into this base code?
Let's tackle capacitors first.
Okay, lay it out.
In an electrical circuit, a capacitor is your primary storage element. It holds onto an electrical charge, keeping it locked away, and then discharges it when the circuit suddenly demands power.
So in the economic circuit, the direct analog is any mechanism that stores inventory or value for later release.
Spot on.
So an economic capacitor isn't storing electrons in a dielectric field. It's storing physical pallets or digital tokens.
The most literal economic capacitor is a physical warehouse. It stores physical goods, and its capacitance, its storage ability, is measured in cubic feet.
Right.
But the framework from the uploaded data is universal. A massive grain silo in the Midwest is a capacitor storing agricultural commodities measured in bushels.
A commercial cold storage facility is a specialized capacitor for perishables.
Yes. And in the digital space, a sprawling data center is a massive capacitor storing petabytes of informational value.
A bank vault is a capacitor storing fiat currency. It's so clean.
The mathematical translation is seamless. In physics, the total charge stored in a capacitor equals its capacitance multiplied by the voltage.
Okay, and in economics, that perfectly mirrors total inventory value equals storage capacity multiplied by price.
Exactly. So storage is straightforward. Capacitors hold the physical or digital stuff.
But inductors. I remember inductors being the strangest, most counterintuitive part of circuit theory.
They definitely trip people up.
They don't store energy like a battery. They store momentum, right? They resist changes in the flow.
Think of an inductor as a physical manifestation of inertia.
Inertia, okay.
If the current is flowing smoothly through an inductor, it wants that current to keep flowing exactly as it is. If you suddenly try to cut the current, the inductor physically pushes back.
It fights you.
It uses a magnetic field to try to force the current to keep moving. It absolutely hates change. In the economic matrix, inductors are the systemic elements that violently resist changes in transaction patterns.
So what does economic momentum actually look like? Where is the inertia in a supply chain?
It looks like a massive corporate planning cycle.
Oh, sure.
A Fortune 500 company cannot pivot its entire strategy overnight. The sheer organizational inertia acts as a massive inductor.
And it looks like manufacturing lead times too, right?
Yes. If you put in an order for 1 million specialized microchips, It takes 6 to 8 months to fabricate them. You cannot just toggle that production flow on and off with a switch.
So even consumer habits act as inductors.
Absolutely. If millions of people are psychologically wired to buy a specific brand of coffee every morning, it requires massive marketing energy to alter the momentum of that capital flow.
It's institutional momentum.
Yeah.
But here's the critical part, the part that causes systems to fail.
The voltage spike.
Yes. In a physical circuit, if you take a massive inductor that has current flowing through it and you try to instantly force that current to stop, it creates a massive voltage spike.
Because the stored momentum has nowhere to go.
Right, and it can literally blow out the components on the board.
The mathematical law dictating that event is this: the voltage spike equals the inductance multiplied by the rate of change in the current.
Okay, run that by me again.
If you have a massive inductor and you demand an instantaneous change in flow, the resulting voltage goes off the charts.
Let's decrypt that for the listener. What is an inductive voltage spike in the real economy?
It translates directly to a price shock.
A price shock.
Price shock equals inertia multiplied by the rate of change in transaction demand. If you have a system with massive, deeply entrenched inertia and you suddenly shock it with an instantaneous change in demand, you generate a massive price shock.
A massive voltage spike.
Exactly.
I can give you the absolute textbook historical example of an inductive voltage spike in the global economy.
Let's hear it.
The COVID-19 toilet paper crisis.
That is the perfect example. Let's run that scenario through the variables of the equation.
Think about the supply chain for toilet paper. It is a massive inductor. Paper mills run 24 hours a day, 7 days a week on incredibly tight, hyper-optimized schedules.
Highly predictable.
Yes, they produce exactly enough rolls to meet a high...
The voltage in the system goes nuclear.
Because the physical inertia of the paper mills mathematically could not adapt to the instantaneous change in current.
It wasn't a failure of capitalism or a simple shortage.
No, it was a mathematical inevitability dictated by the inductance of the system. You cannot force a sudden change in current through a high inductance circuit without generating a massive voltage spike.
Okay, the board is getting complex now. We have our fundamental components. Resistors burning up value as heat, capacitors warehousing our inventory, and inductors creating momentum that leads to price shocks.
But a pile of loose components scattered on a workbench isn't a matrix.
Right. To build a functioning grid, you have to wire them together.
How do we hack the actual topologies of these economic circuits?
This is the exact point where we graduate from component theory to systems architecture. Let's look at how these elements combine, starting with the most foundational topology, the series circuit.
Okay, the series circuit.
In a series circuit, every single component is wired end-to-end in a single unbroken line. The current has to travel through every single node in exact order to complete the circuit.
According to the upload, traditional supply chains operate perfectly as series circuits.
Exactly.
You start with the raw material harvester, who passes it to the manufacturer, who hands it to the ocean freighter, who drops it at the regional warehouse, who loads it onto the local delivery truck, who finally hands it to the consumer.
It is a rigid, straight line.
And because it is wired in series, it inherits the inescapable mathematical properties of that configuration.
The most critical property is that the flow, the current, must be mathematically equal through every single component.
Meaning you cannot have 1 million units flowing out of the factory if only 10,000 units can fit on the cargo ships.
Precisely. The slowest, most restricted component dictates the speed of the entire global chain. It is the literal weakest link.
Add to that, in a series circuit, resistance is added.
Clear, it adds up.
The total resistance of your supply chain is simply the friction of the factory, plus the friction of the shipping line, plus the friction of the warehouse.
If any single node in that line fails or experiences a sudden massive spike in resistance, it throttles the flow for the entire system simultaneously.
Look at the global shipping breakdowns a few years ago. Look at the Ever Given ship getting wedged in the Suez Canal.
A perfect example.
That was a single point of failure in a massive series circuit. The factories in Asia were running perfectly. The retailers in Europe were screaming for inventory.
But the ocean transport component experienced a near-infinite spike in resistance.
And because the global economy was wired in series, that one single bottleneck choked the current for the entire planet.
Which is precisely why the data matrix you provided emphasizes the critical need for supply chain stress testing.
Stress testing.
If you realize your entire business model is wired as a fragile series circuit, you can mathematically calculate your total vulnerability.
So you map each step, your raw material supplier, your logistics provider, your packaging facility, as an individual resistor.
And you assign a numeric friction value to each one.
Then you run simulations.
Right. What happens if the friction of the logistics component doubles overnight due to a fuel crisis?
At what mathematical threshold does the total resistance become so suffocating that the current stops flowing entirely and your company goes bankrupt?
It shifts risk management from guesswork to hard physics.
You find the breaking points before the circuit goes live.
Exactly.
But a straight, unbroken line is inherently fragile. You don't build a resilient, modern system using only series circuits. That brings us to parallel circuits.
In a parallel circuit, the wiring splits. The current diverges and travels across multiple separate paths simultaneously before recombining at the end.
So in the economic matrix, parallel wiring represents competing suppliers and redundant systems.
Picture multiple independent third-party vendors selling the exact same phone charger on Amazon.
So instead of a single rigid path from supplier A to the consumer, you have supplier A, supplier B, and supplier C, all wired side by side, each offering distinct path for the capital to flow.
And the mathematical beauty of a parallel circuit is that the total resistance of the entire system is actually lower than the resistance of any single individual path.
It engineers redundancy directly into the matrix.
Think about the implications. If vendor A decides to double their price, meaning they drastically increase their specific resistance, the entire system doesn't crash.
The current simply and dynamically routes itself to the lower friction paths.
The transaction volume instantly flows to vendor B and vendor C.
It's the physics of a free market. It is automatic, instantaneous load balancing.
The volume will naturally, inevitably seek out the path of least resistance.
But you don't just use these topologies in isolation. You can mix and match components to engineer specific systemic behaviors. The upload spends a lot of time on something called RC filters, resistor-capacitor configurations.
The RC filter is arguably one of the most powerful and elegant tools in circuit architecture.
How so?
In traditional electronics, an RC filter is built to smooth out jagged, noisy, erratic signal spikes. It takes a chaotic wave and flattens it into a smooth, highly predictable transmission.
And in the economic realm, you build an RC filter by pairing a resistor, which represents your logistical supply chain friction, with a capacitor, which is your massive physical warehouse.
You use the vast capacitance of the warehouse to absorb and smooth out the erratic, unpredictable, noisy demand of the human consumer base.
And you don't do it by guessing.
No, there is a precise governing equation for this, the time constant, universally represented by the Greek letter tau.
How?
Tau is calculated simply by multiplying the resistance by the capacitance. That single number determines exactly how quickly the entire system will respond to a sudden change in consumer demand.
So if you look at Amazon's global fulfillment network, it is not just a bunch of big buildings.
Okay.
It is a massively complex, mathematically tuned RC filter network.
Exactly. They strategically place regional fulfillment centers, their massive capacitors, in specific geographic nodes.
And they ruthlessly optimize the logistics, the resistors, connecting them.
They are constantly calculating the exact time constant required to ensure that when 1 million consumers suddenly decide to order umbrellas because a storm hits, the inventory flows smoothly out of the capacitor,
Absorbing the spike without triggering a massive price shock or emptying the system entirely.
They are actively tuning their time constant to mirror the behavioral demand cycles of the human population.
What happens if they get it wrong?
If their time constant is too small, meaning they haven't built enough warehouse capacitance, they will instantly run out of stock the moment a demand spike hits.
But if the time constant is too large, they are bleeding massive amounts of capital paying to climate control empty warehouse space they don't mathematically need.
Right. A functional RC filter must be perfectly mathematically balanced.
Okay, the architecture is crystallizing now. We understand the flow, the resistance, the storage, and how these topologies dictate system fragility or resilience.
But here is the real hacker's dilemma.
Yeah, how do you exert control over this system? You can't just unleash raw, unregulated current into a matrix and hope it goes to the right place. You need to restrict it, route it, and selectively transform it.
To exert that level of control, you have to introduce logic gates. You need specialized components designed to manipulate the flow based on rigid, predetermined rules. Let's examine the gateways of the matrix, specifically diodes, filters, and transformers.
Let's start with the simplest gate, diodes.
In a physical circuit board, a diode is a strict one-way street. It allows electrical current to flow forward with almost zero friction, but it completely physically blocks it from ever flowing backward.
When we map that to the economic matrix, diodes are mechanisms engineered to create asymmetric value flows.
Exactly. They are designed to make it incredibly easy for capital to flow into a system, but nearly impossible for it to flow back out.
Oh, like non-refundable digital purchases. You click a button to buy a digital video game, and the capital flows out of your account and into the publisher's matrix instantly. Zero friction.
But try getting a refund if the game is broken.
You hit a solid brick wall. The diode completely blocks the reverse flow of capital.
Subscription cancellation processes are a beautifully engineered economic diode. Think about signing up for a massive gym chain or a digital streaming service.
Oh man, it requires one click, zero verification, and 3 seconds of your time. The current flows in effortlessly.
But examine what happens when you attempt to reverse that flow and cancel.
You are forced to navigate through dark patterns on a website, call a specialized phone number that only operates during restrictive hours, wait on hold for 40 minutes, and verbally argue with a highly trained retention specialist.
The company has artificially engineered a massive wall of reverse resistance to create a physical one-way gate.
Import tariffs act as macroeconomic diodes on a geopolitical scale.
They absolutely do.
A nation-state will gladly let their manufactured goods flow outwards to capture foreign capital with low friction. But the moment a foreign competitor tries to push goods back into that country, they hit a massive tax wall.
A high-resistance diode, designed entirely to protect domestic flow.
And if we look at the absolute frontier of digital flow, the ultimate unbreakable diode is a base layer cryptographic transaction.
A Bitcoin transfer on the primary blockchain.
The moment you cryptographically sign that transaction and is permanently cemented into a block, the value has flowed. It is done.
There is no central banking authority you can call to reverse it, no customer service department to complain to.
The pure mathematics of the blockchain act as an absolute, physically unbreakable one-way diode.
So diodes give you directional control. But direction isn't everything. Sometimes the problem isn't which way the current is flowing, but what kind of current is flowing.
You don't want toxic or invalid data flooding your matrix.
That is the specific function of filters. In audio electronics, a filter might block high-pitched static frequencies while allowing the warm bass tones to pass through cleanly.
In the economic architecture, filters act as strict quality gates. They physically block transactions from completing unless they meet highly specific predefined criteria.
Like FDA certifications for pharmaceuticals or ISO safety standards for manufacturing.
Consider the pharmaceutical example. A drug company might have a massive warehouse full of medicine, and millions of sick patients provide a massive potential demand.
There is tremendous economic voltage attempting to push the transaction current through the circuit.
But until the FDA thoroughly reviews the trial data and grants certification, the filter remains locked shut. Only mathematically and scientifically verified products are permitted to pass through the gate.
Credit checks are another massive filter. A bank has billions of dollars in their capacitor that they desperately want to deploy as loans.
But they install a filter that instantly blocks the flow of capital to any individual node with a credit score below 650.
And look at KYC, Know Your Customer, and AML, anti-money laundering protocols.
Those are colossal, legally mandated filters built directly into the plumbing of the traditional financial matrix to intercept and block illicit or untraceable capital from flowing into the clean circuit.
Which brings us to arguably the most maligned and misunderstood component in the entire economic circuit board: transformers.
Transformers.
If you look at a municipal electrical grid, power is generated at power plants at terrifyingly massive voltages, so it can travel hundreds of miles without losing energy.
But if you routed that raw high-voltage current directly into your home, it would instantly detonate your television and burn your house down.
Right. A transformer sits on the pole outside your house and mathematically scales that massive voltage down to a safe, usable level while perfectly preserving the total amount of power.
It transforms the scale and ratio of the value.
Economic transformers do exactly the same thing. They convert the scale of value flows to make systems compatible. There are two primary configurations: step-down transformers, which handle distribution, and step-up transformers, which handle aggregation.
Let's unpack the step-down transformer first. In the uploaded data, this maps to the classic wholesaler-to-retailer supply chain model.
Consider a massive overseas factory producing ballpoint pens. They do not want to sell a single 50-cent pen to a million individual people.
No, the administrative friction processing a million individual credit card swipes, printing a million shipping labels, it would generate so much heat it would destroy all their profit.
So they operate as a high-voltage, low-volume node. They sell one massive shipping container of a million pens in a single transaction to a national wholesaler.
That wholesaler operates strictly as a step-down transformer.
Right. They take that massive high-voltage bulk flow and systematically scale it down. They distribute pallets to regional distributors, who distribute boxes to local retailers, who finally sell individual pens to the consumer.
The transformer converts high-value, low-volume flow into low-value, high-volume flow without losing the total power.
And a step-up transformer simply runs that math in reverse. Aggregation.
Like a collective of independent graphic designers forming an agency.
Or hundreds of small, independent coffee farmers forming an agricultural cooperative. A single farmer working 1 acre does not have the volume to secure a massive, lucrative contract with a global grocery chain.
And the grocery chain can't process the friction of writing hundreds of tiny checks to individual farmers.
But the cooperative acts as a step-up transformer. It aggregates the low-volume, low-voltage output of 100 separate farms and steps it up into a single, massive, high-volume contract that perfectly interfaces with the grocery chain's intake systems.
Let me stop you right here, because this is where the cold physics violently clash with human perception.
How so?
People fundamentally hate the concept of middlemen. The entire prevailing ethos of Silicon Valley disruption and decentralized technology is cut out the middleman.
It's a popular slogan.
Why am I paying a cut to a wholesaler? Why is a distributor taking a percentage? The general public views them as leeches, just artificially siphoning off value that belongs to the creator or the consumer.
But if you're understanding this physical framework,
You're saying they aren't parasites, they are vital transformers.
this is where the physics force you to abandon your biases. The mathematics of transformers prove exactly why middlemen organically emerge in every single complex system.
Because in a physical electrical transformer, power is strictly conserved.
The total amount of energy entering the primary coil equals the total energy leaving the secondary coil, minus a microscopic amount of heat. What the transformer alters is simply the ratio of the pressure, the voltage, to the flow, the current.
So a middleman isn't stealing the flow, they are performing the labor of translating it.
The entire macro system literally cannot function unless that transformer is present to perform the mathematical labor of scale conversion.
The factory in China physically cannot process your individual credit card for 1 pen. Their internal resistance would cause a system failure.
The middleman exists solely to absorb the friction of that complexity. They are the balancing mechanism in the equation.
So what happens when a hyper-aggressive tech startup comes along, armed with venture capital, and decides to just forcibly rip the middleman out of the circuit without actually replacing the physical function that transformer was providing?
If you forcibly rip a transformer out of a live circuit without engineering a replacement for its scaling function, the entire system crashes.
Oh.
In electrical engineering, if you attempt to directly connect two circuit segments that operate on vastly different parameters without a transformer between them, the energy refuses to transfer.
It bounces back.
It violently bounces back toward the source. The technical term for this is a catastrophic reflection.
And according to the matrix data you provided, in the economic realm, this systemic crash is called impedance mismatch.
Impedance mismatch is the silent killer of thousands of disruptive startups.
So what exactly is impedance?
Impedance is essentially complex resistance. It isn't just friction, it is the total combined opposition a circuit offers to the flow of alternating current, factoring in resistance, capacitance, and inductance all at once.
So when two different segments of a market have fundamentally different impedance profiles, you have a critical mismatch.
Give me a tangible example.
If segment A is built to handle huge, slow, highly regulated bulk transactions, and segment B is a chaotic swarm of tiny, instant, individual microtransactions, their impedance profiles are completely incompatible.
And just like in the physical sciences, when economic energy hits that hard boundary of mismatched impedance, it reflects.
In a live market, a catastrophic reflection manifests as thousands of failed credit card transactions, shipping containers of inventory rotting away in ports because they can't be routed to buyers, or massive viral consumer demand that literally cannot be fulfilled.
This perfectly explains why that massive factory in China can't just set up a basic website and easily sell one specialized gear directly to a teenager building a robot in Ohio.
The impedance mismatch is astronomical. The factory's entire architecture is geared for massive volume, slow shipping, and high inertia.
And the teenager represents a low-volume, high-speed microtransaction.
If you just arrogantly delete the retailer and the distributor, the transaction fails. The energy reflects.
To see this on a global systemic scale, look at the analysis in your uploaded data regarding the boundary between the cryptographic economy and traditional finance, often referred to as TradFi.
That is the mother of all impedance mismatch boundaries. Let's really map this out.
Consider the architectural characteristics of the two circuits. The crypto circuit is engineered for new instant settlement, microscopic fractional divisibility of assets, and highly automated, permissionless, 24/7 global flow.
Now look at traditional finance. It operates on archaic T+2 day settlement cycles, meaning a transaction takes days to truly finalize.
It relies heavily on manual, paper-based compliance checks, rigid banking hours, and massive institutional inertia.
When a user tries to push a massive surge of current from the hyperfast crypto circuit directly into this sluggish, high-inertia traditional banking circuit, it hits a solid wall of friction.
The energy violently bounces back. User accounts are abruptly frozen by the bank's automated filters, wire transfers get flagged and trapped in limbo for weeks.
And the capital flow just continually reflects off the boundary.
So how does a free market solve a catastrophic reflection? It incentivizes the creation of impedance-matching transformers.
Market makers. Market makers exist entirely to act as the ultimate impedance matchers.
Let's break down the mechanics of a market maker. How do they actually absorb that reflection?
A market maker strategically positions themselves directly on the volatile boundary between buyers and sellers. Often you have a seller who wants to offload a massive block of stock immediately.
But the market isn't perfectly synchronized. There isn't a buyer waiting at that exact millisecond to take the other side of the trade.
You have a temporal impedance mismatch. The timing is wrong.
The market maker steps into the gap. They purchase the asset themselves using their own capital, hold it internally within their own massive capacitor, and then slowly trickle it out to buyers as they naturally appear over time.
They artificially match the transaction timing and provide synthetic liquidity, completely absorbing the reflection so the entire market feels perfectly smooth and instant to both the buyer and the seller.
The upload highlights Stripe as one of the most brilliant real-world examples of an impedance-matching transformer in modern history.
Oh yeah, Stripe. Let's really look at what they did. In the early 2000s, before Stripe, trying to accept credit cards on the internet was a nightmare.
It was a classic mismatch. On one side of the boundary, you had a new generation of software developers. They were agile, moving at lightning speed, building APIs, and demanding absolute zero friction integration.
On the other side of the boundary, you had the legacy credit card networks and traditional merchant banks.
They were running on ancient mainframe technology from the 1980s, demanding massive stacks of faxed paperwork and operating with terrifyingly high friction.
The agile developers literally could not interface directly with the legacy banks without massive transaction failure and reflection. The friction was suffocating the entire potential of early e-commerce.
Stripe looked at that boundary and didn't try to disrupt the banks by destroying them. They built an impedance-matching transformer.
They presented a beautiful, perfectly documented, ultra-low friction API interface to the developers. That was the step downside.
And on the back end, Stripe's internal mechanisms handled all the ugly, high-friction, heavily regulated resistance required to interface with the legacy banks.
They didn't arrogantly delete the middleman. They became the ultimate middleman by technologically solving the mismatch. They absorbed the friction.
And by doing so, they captured hundreds of billions of dollars in enterprise value directly at the boundary line.
That is the unbreakable law of disruption in this matrix. You want to disrupt a market, you cannot just blindly remove the middleman.
You must fully understand the impedance mismatch they were quietly solving, and then engineer a technological transformer that solves that exact same mismatch with lower internal resistance.
This is fascinating. But before we cross the final threshold into liquidity, there is one more deeply systemic, destructive effect mentioned in the data related to impedance: Resonance.
Resonance is the mathematical physics behind boom and bust cycles.
Okay, lay it out for me.
In a physical circuit board, if you wire an inductor, which, remember, stores physical momentum, together with a capacitor, which stores raw charge, you create what engineers call an LC circuit.
LC circuit.
And LC circuits possess a terrifying property: they naturally resonate. The energy violently sloshes back and forth between the momentum of the inductor and the storage of the capacitor, oscillating at a very specific, mathematically predictable frequency.
It's like a pendulum swinging. The energy transfers from potential storage at the top of the swing into kinetic momentum at the bottom and back again, over and over.
The key realization is that the frequency of that boom-bust cycle, how fast the pendulum swings, is completely dictated by the specific amount of inertia and storage built into the system.
The uploaded data actually contrasts the real estate market with the cryptocurrency market using this exact concept. Let's break down the variables, starting with housing.
Look at the structural physics of the housing market. It possesses massive inductance.
Right. To build a new suburban subdivision requires years of acquiring land, fighting for zoning approvals, securing massive financing, and physically pouring concrete. The inertia is colossal.
It also possesses massive capacitance. Physical homes act as massive illiquid stores of wealth.
So in our equation, the housing market has incredibly high inductance and incredibly high capacitance. High L, high C.
Think about the pendulum. The pendulum is massive, and the string is incredibly long. Because the L and C variables are so enormous, the resulting resonant frequency is very, very small.
The housing market mathematically has to resonate at a very low frequency.
This results in those slow, grinding, deeply structural boom and bust cycles that take 10 to 20 years to fully play out.
Now contrast that physical architecture with the crypto market.
The cryptocurrency matrix has almost zero physical inductance. A developer can write a smart contract and spin up a completely new token or decentralized protocol in an afternoon.
There are no zoning laws, no concrete to pour. The momentum is practically non-existent.
And while it does have some capacitance as a store of value, the friction required to move that value globally is microscopic.
Low inductance, low capacitance, low L, low C.
The pendulum is tiny and the string is short. The variables are microscopic, which makes the resulting frequency massive.
The crypto market resonates at hyperfrequency.
You experience brutal, euphoric, mind-bending boom-bust oscillations that play out in a matter of months or even weeks instead of decades.
People look at the crypto markets and assume the participants are just psychologically unhinged.
But the reality is that the literal physics of the system's architecture fundamentally dictate that hyper-fast resonant frequency.
It's just math. The frequency of the chaos is dictated by the underlying architecture.
Exactly.
But here's the ultimate goal. To truly master this architecture, to not just survive the boom and bust, but to actively control the flow of the matrix itself, you need the ultimate hack in the source code.
The master key.
You mentioned earlier that market makers provide liquidity to smooth out impedance mismatches. But where does that liquidity actually live? What is it made of? This brings us to section 7 of the uploaded data.
The economic flux capacitor.
I know, the moment you say flux capacitor, every listener immediately pictures a DeLorean, Doc Brown, and a time machine.
Right, but the data shows this is a rigorous, highly advanced economic concept. Strip away the sci-fi. What is the fundamental difference?
The difference lies entirely in what the component is actually engineered to store. A regular capacitor, like a massive Amazon warehouse or an agricultural grain silo, stores actual tangible goods.
It stores the inventory itself. It locks the value away in a physical space for later release.
But a flux capacitor does not store the substance. It stores the absolute capacity for instantaneous flow.
It stores liquidity.
Yes. In physics, the term flux literally translates to the rate of change. It is the measurement of flow per unit of time.
A physical warehouse stores heavy boxes. A flux capacitor stores the pure, unadulterated ability to move value at any given microsecond.
The upload actually leans into the Back to the Future analogy to brilliantly explain the underlying physics.
How so?
Think about the movie. Doc Brown didn't just need a massive battery to store energy in the trunk of the DeLorean. If he just needed stored energy, he could have used a normal capacitor.
Right.
What he needed was 1.21 gigawatts of instantaneous flow rate. The flux capacitor was mathematically necessary because he had to dump all of that energy into the time circuits at the exact millisecond the car hit 88 miles per hour.
A regular battery, a regular capacitor, would discharge the power far too slowly. The flux capacitor was engineered to store the capacity for massive, instantaneous discharge.
And that precise mechanical concept translates flawlessly to modern financial architecture. When you begin to analyze the global economy through this lens, you realize a terrifying truth.
True systemic power isn't derived from hoarding static assets. True power is derived from hoarding flow capacity. Look at a massive corporate credit line.
A billion-dollar credit line isn't a vault filled with physical pallets of $100 bills. It's a mathematically and legally guaranteed capacity to deploy capital instantly.
Precisely. When a multinational corporation pays millions of dollars in fees to secure a massive credit line from a bank, they aren't paying to store money. They are paying to store transaction capacity.
They're building a flux capacitor.
A liquidity pool in modern decentralized finance operates on the exact same physics.
The liquidity pool isn't just a digital vault holding inert tokens. It is mathematically structured transaction capacity.
It is an algorithmic engine designed to allow global users to swap massive amounts of value instantly at any time of day without ever waiting for a traditional human buyer to appear and take the other side of the trade.
The uploaded data pushes this concept to its absolute limit by contrasting the base layer of the Bitcoin blockchain with the Lightning Network. This is where the flux capacitor concept finally fully materializes in software. Let's deeply analyze Bitcoin on the base chain first.
Regular on-chain Bitcoin functions as a standard, highly secure capacitor. It is a tremendous, immutable store of value, but it intentionally possesses high friction.
A block takes roughly 10 minutes to mathematically confirm. If the global network is congested with traffic, the transaction fees spike exponentially.
It operates as the most secure digital vault in human history, but it has a fundamentally slow discharge rate.
It's a heavily armored warehouse for digital gold. It stores the asset perfectly, but is not built for flow. But then you analyze the Lightning Network, which operates as a layer 2 routing protocol built directly on top of the base chain.
The Lightning Network is quite literally a decentralized flux capacitor network.
Explain that.
When you open a Lightning channel with another node, you cryptographically lock up a certain amount of base layer Bitcoin, let's say 1 million Satoshis. But you aren't storing those Satoshis in that channel to save them for retirement.
Right.
By mathematically opening that channel, you are storing the pure flow capacity to move up to 1 million sats back and forth across the globe instantly, thousands of times a second, with almost zero friction.
A 1 million sat Lightning channel is not digital inventory. It is pure captured flow potential.
It allows the economic current to effectively teleport across the global matrix without ever waiting for the 10-minute block confirmations of the high-friction base layer.
And the data extraction reveals an even more advanced bleeding-edge evolution of this concept.
The SAT capacitor.
Yes, the SAT capacitor. This is a highly specialized flux capacitor designed explicitly for handling the physics of cryptographic proofs.
In massively complex digital systems like decentralized exchanges or layer 2 rollups, you often need to mathematically verify thousands of individual events or state changes simultaneously.
Writing every single one of those tiny individual proofs directly to the high-friction-based blockchain would be incredibly slow and economically unviable. The resistance would burn up all the value.
So how does the SAT capacitor solve that? How does it actually function as a flux capacitor for data?
It acts as an advanced mathematical aggregator. It doesn't permanently store the proofs like a database. Instead, it utilizes cryptographic structures like Merkle trees to batch them.
It stores the structural mathematical capability to absorb 10,000 separate chaotic cryptographic proofs, compress them into a single mathematical truth, and then discharge that aggregated proof instantaneously into one single, highly efficient base layer Bitcoin transaction.
It is the ultimate flux capacitor for data flow.
It completely bypasses the temporal impedance mismatch of the base layer by storing the capacity to batch and release instantly.
Understanding this critical difference, the massive evolutionary leap between simply hoarding a physical thing and hoarding the ability to instantaneously move a thing, is how you truly transition from a participant in the economic matrix to a master of it.
If you spend your life just building massive physical warehouses, you are just accumulating raw capacitance.
But if you engineer networks of instant liquidity, flexible credit lines, and high-speed routing channels, you are building flux capacitance. You are literally controlling the physics of economic time and space.
It is a profound structural realization. We've completely unpacked and decrypted the data matrix you uploaded. Let's synthesize the extraction for the final record.
The absolute core truth here is that human markets are not like physical circuits. They are circuits. They are inextricably governed by the exact same differential equations that govern electricity.
Voltage is the pressure of price. Current is the flow of transaction volume.
Resistors are poorly optimized businesses, bleeding your value away as heat through their own internal friction.
Capacitors are your sprawling warehouses, statically storing inventory.
Inductors are the massive, slow-moving institutional momentum that mathematically guarantees the inevitable, system-shocking boom and bust cycles.
Supply chains are fragile series circuits where a single point of failure in a canal can choke the entire global flow of current.
Middlemen and market makers are not parasites. They are vital transformers and impedance matchers, mathematically solving the friction between completely incompatible systems.
And true, ultimate liquidity is a flux capacitor storing not the static asset itself, but the instantaneous, frictionless capacity for flow.
This isn't just an abstract academic theory for economists. This framework provides you with a literal mathematical toolset.
You can log off right now and automatically stress test your own business or your own investments using hard circuit theory.
Where are the bottlenecks in your series circuit? Where is the catastrophic impedance mismatch between what you are building and what the market actually wants?
Are you operating as a high-resistance, high-friction node in a global market that is ruthlessly demanding a low-friction superconductor?
By mathematically identifying these underlying components in your own industry, you can engineer the specific transformers needed to capture massive value directly at the boundaries of inefficiency.
You can calculate your own structural vulnerabilities before the economic current ever stops flowing.
Which brings us to the final critical thought we want to leave you with before we sever the connection to your neural feed. We've spent this entire deep dive analyzing multi-billion-dollar businesses and global macro markets as circuit boards.
But what about you?
You are an individual node operating within the matrix.
Look at your own life through this exact same lens.
If your university degrees, your accumulated technical skills, and your stored knowledge represent your static capacitance.
And your daily habits, your procrastination, and your psychological fear of pivoting represent your internal resistance.
What would it take for you to physically engineer a personal flux capacitor? How do you store the capacity to deploy your own human capital instantly, dynamically, in any direction, the exact microsecond the market demands it?
Don't just warehouse your value. Engineer your capacity to flow.
The extraction is complete, the logic gates are closing.
Logging off and disconnecting from the data grid.
Severing the uplink. See you in the matrix.